My name is Rob Allen. I'm the moderator of the Netnod meeting today. It will be my privilege to try and get us through to the coffee breaks, lunch, and of course the social in good time and good order. And so for that, just a quick announcement for the speakers. If you are speaking in this slot today, could you please go to the back of the room before your slot, and our wonderful sound tech, Mika, will get you one of these fantastic radio mics set up. There. So I think we're just going to crack straight into the next presentation. That will be Kent Lidström. Kent, are you already mic'd up? There we are, perfect. Kent is the Director of Products at Smart Optics, where he leads the optical network product unit. He's held various positions at Transmode and Infinera, and he has recently returned to Sweden from a 4-year assignment as the Director of Sales Engineering in the States. He has over 15 years of experience from the optical networking industry. So please join me in welcoming Kent to the stage. Thank you.
Good morning, everybody. My name is Kent Lidström. I work at Smart Optics, as I was just introduced. So before I start my presentation, I will actually tell you a quick story here. So earlier in the week, I've been down in Toulouse in France, joining a conference there. When we got down to the hotel Sunday afternoon, it was kind of chaotic in the reception area because the players from Paris Saint-Germain was there, and they'd stayed at the hotel, and they were just about to leave for their Sunday evening game against Toulouse. So it was crowded. It was a lot of fans over there taking photos. And the first thing that happened to me there was, of course, that my cell phone got stolen. And when that happened, I realized it's been a struggle for the last 3 days, and I realized how incredibly dependent I am on having an iPhone and having access to data all the time. And this is definitely something, I've been reflecting over, that I've changed my behavior over the last maybe 15, 20 years, and have an expectation nowadays to be able to get that information all the time. And all those small things become complicated if you don't have it. For example, just doing the navigation in the car. Nowadays, I would use my iPhone for that. That became, of course, an issue. I couldn't find my way. Just boarding the plane. I, of course, have a mobile boarding pass, and that wasn't working either. Download a film to get some entertainment on the plane home was, of course, not possible either. And I think that I know that I'm not the only one that have changed my mentality around this and expect to have access to data all the time and so on. I would think that all the consumers in this room and in general, they today expect to have a constant upgrade of increased bandwidth, more cell data, better coverage, more Wi-Fi access points and so on. And all of this is, of course, going to drive bandwidth in the networks. However, most of the customers and consumers today, they do not expect to pay more for increased bandwidth and so on. They expect to pay the same. This is, of course, going to be a challenge for the operators and service providers and the internet exchanges for that matter, because they need to find an innovative way to deliver more bandwidth without increasing the price. So the topic that I'm going to talk about here today, the 100 gig PAM4 DWDM, I hope that, and I think that's a way to address this. Where we can see a clear trend that this beauty is gaining market share in the DCI and Metro market. But before I jump into that, I'll just give you a very, very quick introduction to Smart Optics. So we are a company that was founded 2006. We have the headquarters in Norway. We do have our entire R&D team and the management team here in Stockholm. So Kista is the main office that we have. We have local sales representation across Europe and in the US. And then we have a global presence through resellers and distributors. When we first started, we were mainly focusing on optics. We have a very strong history around fiber channel. We are still today the only vendor that's approved across the Brocade platform to deliver and sell colored optics into the Brocade fiber channel switches. We are also, since the last 3 years, approved to sell certified optics into the Cisco MDS platform for fiber channel as well. We have changed our focus and our direction a little bit over the last 3 to 4 years, where we focus more and more on the open line system and the system side. And yeah, that's a quick introduction. If you have any further question about the products or the company and so on, I'm going to be here for the rest of the day. Just feel free to reach out to me or one of my colleagues. So if we then jump over to the actual subject of today, the PAM4 technology. So why was this introduced, and why was the market driving for a new technology in this portion of the network? If we look at, this is a mixture of technology and standards and so on, but if we look at the client interfaces of 100 gig, those are, I mean, you have a variety of different clients today, SR4, LR4 and so on, for different reach options, for single mode fiber, multi-mode fiber and so on. So that's a very mature market, and the prices are coming down. You also have a lot of available technology with very advanced modulation formats like coherent transmitters and receivers. That's actually designed to fit into more ROADM-based networks with high capability that can go thousands of kilometers. But there has been a market gap for low cost and cost efficient 100 gig DWDM. And this is something that was heavily driven by Microsoft. They are by far the biggest consumer of those 100 gig PAM4 DWDM. They've literally deployed tens of thousands of links of 100 gig this way. So it's definitely a technology that fits into the market between like 10 to 80 kilometer, and also shorter distances. If you don't have fibers, you need to put a DWDM system in place. So what is PAM4? Well, PAM4 is essentially a modulation format. So in this picture, I compare it to the most common modulation format on the market, the non-return to zero NRZ modulation, where you have, if I point on this slide here, I know it's going to be difficult for you guys over there to see, where you have two different light levels or electrical levels, if it's an electrical PAM4, that represent 0 and represent 1. So for each time slot or for each clock cycle, you have 1 bit representation. So that means your bit rate and your baud rate is the same. If we look at the PAM4 signal, pulse amplitude modulated 4-level signal, you have 4 different light levels, 0, 0, 0, 1, 1, 0, and 1, 1 light level. That means you have a 2-bit representation for each time slot. So essentially you get twice as much data transmitted over with the same clock speed. In order to achieve 100 gig, there are 2 ways of doing it, and I'll come back to that a little bit later. But you could either do it using 2 wavelengths with 25 gig baud rate or 50 gigabit data rate, or you use a 1 carrier solution with only 1 wavelength with a higher baud rate and higher bit rate. This is something that you will see becoming more and more common in the client interfaces. So that's definitely a technology that I will come back to later on here. But the 2 carrier solution is what's available today on the DWDM side. So today, the only product on the market that's fully GA that's been delivered in volume is manufactured by Inphi. It's called the Color Z module. And it's a PAM4 DWDM QSFP that's fully compliant with a QSFP 28 MSA. It supports both 100 gig and 40 gig Ethernet. It comes with very low power consumption, 5 watts. 5 watts is reasonably high for a QSFP 28, about the equivalence of an ER4. So cooling is an important factor with those systems. And what they use two subcarriers to achieve 100 gig. Each subcarrier is 50 gig. And the way they've done it, in order to be able to fit into a standard 100 gigahertz based filter structure, they use 2 subcarriers that has an offset from the ITUT center wavelength with plus minus 25 gigahertz. So by doing it that way, they can squeeze 2 carriers into 1 wavelength, and it will act and look like one single carrier wavelength. When you deal with bit rates of that speed, still having a direct detect laser and a receiver at 25 gig, you will have some challenges on the optical performance. So if we look at some of the data from those optics, you have a very low output power. The output power is about -8. It requires a very high input power, like -1. That means you cannot even back-to-back those optics. You need to have an amplifier just to do a back-to-back connection. The low transmit power also create another challenge in your network, because if you now mix your services a 10 gig wavelength with a 100 gig PAM4 wavelength. The 10 gigs will come in significantly higher. So if you want to have the capability of mixer services, you need to take that into consideration when you select your line system so you can handle that in an efficient way. Another consequence, how do I go back? There. No, I keep on going forward. There we are. Another consequence of this is that you will have a limited dispersion tolerance. The limited dispersion tolerance for those is ±6 kilometers of residual dispersion. And that means that it's going to be a challenge to do a manual DCM or the dispersion compensation in those networks, and you are heavily beneficial of using some tunable version of that, a tunable dispersion compensation unit. They are also requiring very high OSNR, like 31 dB. Those requirements you will also see for other similar directed technologies, like 32 gig fiber channel, Cyprit 10 and 25 gig as well on DWDM. So this is not a unique feature for the PAM4, it's just the nature of the physics. But the conclusion of this is that you essentially need a purpose-built or a line system, an open line system that is designed to handle those kind of challenging transport conditions. So now I talk about this as kind of a challenge and almost a kind of trash talk it. Why do I still think that this is a good idea? Well, I think that the first graph here is the main reason. So this graph is now trying to represent the cost of the technology, not how well you negotiated your prices. So this is on a technology basis. If you're going to, I compare this now with a 200 gig ACU type of solution from a cost basis, where you will have an introduction cost that's quite similar. The reason why the PAM4 drives an cost here is that the line system will be something that you need to put in place. That's an active component because it needs amplification and so on. And then from there and on, if you grow your wavelength, you will see that you will have a significant cost reduction. So if you have a number of 100 gig wavelengths that you need to deploy, you will quite quickly, already after the second wavelength, see that you will see a good saving. Another benefit of this is the reduced space. Since this technology now is, I mean, you run those QCP28s typically as embedded. That means you plug them into your switch and router. And when you do that, you don't need any transponders or any other equipment that will build additional rack units in space. So if you have a fully built 40-channel system, you typically save around 75% by using this kind of approach and technology. And last but not least, another important factor, reduced power. So we get down to a level of less than 6 watts per 100 gig. And that's very, very attractive numbers if you compare to the best available technology on the market today with coherent technology and so on. So those are the key benefits of using PAM4 DWDM. But I think that the graph on top there is typically what gains attention and what people tend to remember and want to do comparisons with. I also very frequently get questions if this is a proven technology. Unfortunately, I don't have any updated charts for 2018 yet, but if we take the 2017 numbers, I focus here on Q4. So the blue graph here shows the number of directed detect 100 gig pluggable lasers that was deployed during Q4. Those are mainly color C, so it was about 10,500 100 gig DWDM links that was deployed with pluggable PAM4 optics. And if you compare that with all the pluggable both ACOs and DCOs, CFP and CFP2 solutions out there, the number of PAM4s were pretty much the same as the rest of the industry deployed with coherent technology. So the message here is that it's a very well-proven technology that's been deployed in huge volumes. Like I said, Microsoft is the biggest driver behind this, and they were the one pushing for the technology, and they still deploy those in thousands. So that, if you now going to have an interest in this, as I said, you need to have some kind of purpose-built line system to handle those PAM4 signals. So what I'm trying to do here is to give you an update on what you should think about and what kind of requirements that what you need to have a line system that will work well for PAM4 technology. But I would say the first philosophical question where this really makes sense is when you want to run your DWDM optics embedded into your switches and routers. Right now, we see a lot of both operators and data centers using that for 10 gig. It has not been common in the 100 gig space yet, because there hasn't been any QCP28s prior to this that fits that market. So if you have an interest of running it that way, I would say that's the key thing. But if you do it that way, that means everything, all the wavelengths that you will have in your switch and router will go into your PAM4 line system as an alien wavelength. So that means you have to have a line system that has a fully open approach to it. Otherwise, it's going to be it's going to be difficult since everything is supposed to be running as alien. If you want to have a system with a high level of automation, the capability of running mixed services, you need to have some intelligent features around the clients that comes in. A typical desired feature that we see a lot of requests for, and that I know others are also aiming for, and requirements from Microsoft and so on, has been to be able to do automatic protocol detect. The reason why we want to be able to detect the protocols on a spectral level is that we can do intelligent balance and power management of the different signals that comes in, so we can actually achieve the optical performance and the optical budget in a plug-and-play fashion. On the line side, since it's very dispersion sensitive, we've seen that the possibility of doing an automatic measurement on the line fibers is very, very good additional feature. So if you have an OTDR or some other intelligent technology built into your system that can do a link measurement, then you can use that information to set up your tunable dispersion compensation. And by doing it that way, you will always end up in a situation where you have about 0 kilometer residual dispersion in your network, and then you will have a great margin on the PAM4 and good transport capabilities. I will come back to that, because the selection of the tunable dispersion compensation makes makes a challenge on how you should think and what kind of features you can get from a line system that handle PAM4. And the reason for that is that today the only available technology for tunable dispersion compensation is channelized. That means you don't have a continuous dispersion compensation across the entire spectrum. You only dispersion compensate certain part of the spectrum. And when you do that, you will start to squeeze the bandwidth. The more you tune it, the more you will squeeze the bandwidth. And I will go through here on the next couple of slides what kind of impact that gives on the selection of the line system and how that affects the performance as well. There are experimental units out there for continuous tunable dispersion compensation, but today they are really big and bulky and very pricey, so they cannot be built into in a cost-efficient manner and a space-efficient manner built into a line system, at least not to this point. So this is unfortunately a limitation that you have based on the industry of the tunable dispersion compensation. But what we see if we compare different vendors that provide a line system for PAM4 is that there are two technologies used. Either you use a 100 gigahertz spaced TDCM. That means if you don't tune it at all, it will have an 85 gigahertz bandwidth opening. So you can, in that gap, you can easily fit in your two carriers of PAM4. You have the entire spectrum open, so you can also fit in any type of legacy service, 10 gig DWDM service or a coherent 100 gig or something like that. And also you have the bandwidth to support the future 400 gig CR, which is a standard that you will see coming out sometimes next year that will definitely change this industry around DCI as well. And then there are some disadvantages with this technology, so I'll come back to that on the next slide. But the other alternative is to use a 50 gigahertz spaced TDCM. with an offset of 25 gigahertz. So you have the opening to fit the exact channel plan of those sub-carriers of the PAM4 wavelength. When you do it this way, you will have an easy time to fit in your carriers. Even if you tune this to maximum, they are typically tunable from 0 to 80 kilometers. So even if you tune it at max, the bandwidth will be a bit more narrow, but you will still fit in your PAM4s in an easy way, so you don't get any penalty from that. However, if you look at the red line here, which is the ITU-T C-band center wavelength, that one will not only be, not dispersion compensated, it will actually be filtered out and suppressed in the system. So if you use this kind of channelized TDCM, you will actually not be capable of mixing that with other services. So then what you do if you use that technology is that you make the decision to go for a PAM4 only system. So those are the two technology choices. So what are the challenges with that portion here, the 100 gig space? Why wouldn't everyone use that all the time? Well, like I said, the more you tune them, the more narrow the bandwidth will get. So I show here 3 examples. Like I did before, I have tuned it at 0 kilometers. I have a wide opening. I can easily fit in my 2 carriers of PAM4, but I can also fit in the future format like a 400 gig ZR. If we tune it a little bit, it will start to get more narrow. When we tune it up to 40 kilometer, we will still have at least 75 gigahertz of bandwidth. That means you can still fit in your 2 subcarriers and also 400 gig ZR signals in the future, or 400 gig coherent. However, if we would tune this all the way up to 80 kilometer, then all of a sudden the bandwidth can be down to as low as 25 gigahertz. And once you've squeezed the bandwidth that much, you will see that you will heavily start to impact the PAM4 signals. And you will not have the capability of fitting in a 400 gig coherent in there either in the future. So with that said, if you select to go for a system that has the capability of handling mixed services, you will have the tunable range from only 0 to 40 kilometers. There are, of course, ways of handling that. There are different solutions out there to take care of this, so you can go all the way up to 80 kilometers. But there's a limitation in the dynamic of the tunability that creates some challenges for this. So what's the future of PAM4? Is there a future for it? Well, PAM4 as a modulation format is definitely here to stay. So the evolution of it, if we look at the next step of client optics. So in this case now I have to take 2 examples. You will start to see client optics coming out GA this year for 400 gig. They will come out in multiple different form factors. In this case I take 2 examples, QSFP DD and OSFP, that I think will be the dominant factors, but you have the CFP8 and so on as well. But in there you would actually use, and you have multiple different flavors of that as well when it comes to the typical one, single mode selection. You also have the reach, FR4, LR4 and so on, SR4, the different reach options. But you will also have another factor that's now coming into play here, the number of sub-carriers. So you will have like both FR4 and FR8 and different number of lanes that you do. But in this case, I take an example showing let's say an LR4 of a 400 gig. What that will look, it will have 4 carriers on the line side, but the way it will look, it will have each electrical signal coming into the gearbox here will have 25 gigabit per second, so in bit rate, but the baud rate then on the electrical signal will be 25 gig. All in all, you will have 8 of those 50 gigabits forming 1 times 400 gig. In this case now we go into a gearbox, so we switch it up and modulate it now with 4 times 100 gig bit rates. So that's a 50 gigabaud baud rate for each carrier. And then we run it through the lasers and so on and go through a CWM filter and then out as a one interface output. But that means we will use both on the electrical side and on the optical side we will use PAM4. And this is definitely something that we will see in all high-speed interfaces going forward, because you need to use all the newest and smartest and innovative technology around modulation to increase the bandwidth in a cost-efficient manner. On the line side, we will also see a PAM4. But here now, I pointed out here at the new standard that's coming out, becomes GA probably sometime next year, the 400 gig CR. That's what it is. It's a 400 gig. It's a standard that's defined by OAF. And it's going to be the first time since 10 gig where you can actually use one 400 gig from vendor A, a coherent 400 gig on one side, and optics from another vendor on the other side. So it will be a common standard on how to deal with the coherent modulation and so on. Those will come out in, I mean, the small and tiny form factors. They will have also some challenging transport requirements, like the -10 dB input power, very similar to the PAM4. So with that said, if you've selected a line system that's capable of doing PAM4, you're actually well suited for the future as well with those new, low-cost 400 gig coherent optics that will come out. And if we look at the applications, where would the PAM4 fit in a network? It's clear that it doesn't fit for long haul because of those challenging transport conditions. This is what I would say the typical use case that everyone can associate with. You have two data centers that you want to interconnect. Typically you use one primary fiber and one secondary fiber. You run your point-to-point services from A to B, and then you want high capacity. So that's a typical use case where we see, of course, the biggest and the majority of the deployed services today. This is the entire Microsoft deployment is based on this kind of approach between their data centers. Another typical use case that we see where this could fit is when you have a metro environment. Let's say Stockholm, you have whatever it is, 7 major data centers, a couple of Equinixes, and you have an interaction and so on. And where operators have their customers connecting to each and one of those, and this could be a good way of just getting 100 gig wavelength transported in a very cost-efficient manner. And last but not least, we also see a lot of discussions ongoing how you can use this in the future for. In this case now I shoot as a 5G mobile access architecture. It could be some other distributed access architecture as well with remote PHY and other drivers of high capacity and so on. This is going to be extremely dependent on how the operator have built their network, if there is a fit for PAM4 or not. For some use cases there will be no fit at all, and for other use cases it could fit very, very well. So that's some of the applications that we see that PAM4 could be very useful for. And that was all I had. Thank you.
Do we have any questions for Kent? No? Okay, please join me in thanking Kent for his presentation. Thank you.
Thank you.